Eu queria uma grande salva de palmas para Venkatsumania. Oh! Oh!
Thank you. Thank you, thank you. It's such a great pleasure to be here. I want to thank the conference organizers for having me here. Thank you all for being here as well. So I want to talk about programming. How many of us here are programmers? Yeah, I'm in the right place then. Well, I was on a flight, and generally, when I sit down on a flight, I immediately start coding. There was a lady next to me, and she looked at me, and she said, I cannot believe that humans are still doing this. And I stopped what I was doing and said, excuse me. And she said, I cannot believe that humans are still doing it. And what she meant was that we're still writing code. What surprised me was she thought I was a human. But the point really is, and then I asked her what she does, and she said she once upon a time was a programmer. But this was in the days of punch cards. And I said to myself, that was a long time ago when humans used punch cards to program. We've come a long way since then. But I want to talk about where are we heading when it comes to programming. Well, they say that things change really fast in the field of computer programming and computer, in general. But I want to look back at where we were to see where we are going. Well, we've come a long way, certainly, when you look at the machines that we have been using for quite a while. And I remember using most of these machines and a few things earlier. My earlier days were in using VAX VMS systems, where all you have is a terminal. You don't have a machine in front of you. And you type into it, and the code executes in some remote mainframe system. And then we went all the way to having personal computers. And now we are back to using cloud, where you type something and it runs elsewhere. So we come in a full cycle if you really think about it. And so we've seen an evolution of technologies and computers over time. But this reminds me of an experience. I was at the store with my family, and we were just walking through the store, and my wife looked at correction fluid. And then she paused and said, oh, look, the correction fluid is over there. And my son was very curious. He said, what's a correction fluid? And then my wife said, oh, correction fluid is where when people type, they make mistakes, and then they would use the fluid to erase what they are typing so they can type on it again. And he's a very patient kid, so he was listening to it very carefully. And then I shouldn't have spoken, but I said, oh, you know what? When Dad wrote his thesis, it's Grandma who typed the entire thesis for your dad. And so your grandma did all this typing on the typewriter when Dad has to write his thesis. And after listening to all of this, my son quietly asked, what's a typewriter? And that's when I realized that we have come so long that a generation of people don't even know certain technologies that's been around for a while. And then, of course, I tried to explain to him what a typewriter was. It's a machine on which you type, and you put a paper and you spin through it. And he listened to all of this, and he said, why would anybody do this? Why can't you just use a printer? And I immediately ran home before he could come home and went to the closet, and I hid all the floppy disk I had with me, because what if he ever finds out I had a stash of those in my closet? Well, it's fascinating to see how the technology around us has changed quite extensively over the past about 20, 30 years. It's a lot of fun to be growing in this field. I started programming about 35 years ago. And I've been programming for a good 35 years ago, and I program in about 15 different languages. What that tells you is I'm not good in any of those languages. But the point is, I love programming in different languages because it makes me think very differently. It makes me design things very differently. So I'm a huge fan of learning programming languages and applying them, and that's a very exciting way to do things. But in that regard, we can ask the question, a lot of things have changed in the past 50 years. We as humans have been writing code for about 60 plus years, give or take. So if you really think about a lot of human activities, we've been doing that for centuries, but we've been writing code for maybe about half a century or so. So this is a very nascent field compared to a lot of things that are out there. So a lot of things have actually changed in this regard. But what has really changed? Well, I remember growing up with mainframe computers. These were machines that would be so huge that they would fill buildings and they would generate so much heat, if you will. And the amount of power they had was not that much. They only produced more noise and heat for all practical purposes. Today, you and I carry devices in our pockets which are a lot more powerful than some of those machines. And that's a revolution, that's a change that we are all seeing. And we have come a long way. But then I noticed, what are we doing with all this power? What are we doing with all this computing power on our hands? Every single one of us has multi-core processors on our pockets today. And I was curious, what do humans do with all that power? I travel around the world. I'm in a lot of different countries. I'm in a lot of different airports. And anytime I walk through an airport, when somebody is using their device, I want to curiously see what they do with it. And I've come to you to show you the market research I've done. And this is what I found. And I admire the human quest to create new powerful devices so fellow human beings have options like never before to play solitaire. That's what people actually do with all that power, isn't it? This is a kind of a shame if you really think about it. Because every airport I go to, every office I go to, I look at what they do, and they're playing solitaire, right? So, okay, at least it keeps some people off the streets. That's not a bad thing. But the point really is, where are we heading in terms of where we have been? And so the question to that is, how are we really going to program in the new century? How are we going to do this in the new century? What does it mean to be programming in the decades and years ahead? Let's think about this for a minute. How are we really writing code? So here's a little example I want to start with, just to think about what is the mainstream we are doing in terms of programming itself. So here's a little example. I've got a list of names given to me. And what I want to do is I want to print comma-separated names of length 4 in uppercase. A really simple problem, isn't it? It's not a rocket science, a very simple problem. So I want to print comma-separated names of length 4 in uppercase. So how would I do this? Oh, that's very easy, you would think. So I'm going to say int I equal to 0, I less than. Oh, is it less than or equal to? We're never sure about it, isn't it? And then you say over here, names dot. Oh, is it length? Is it size? Is it count? Because if we had a standard, we will get our work done very easily. So in this case, it's a size. And then I plus plus, or is it plus plus I? We have to make all these decisions. And then when you realize that, gosh, that's a simple way to do this. Why are we struggling with this? Let's simply say string name that comes from names after all. And then we can simply print out name over here, dot to uppercase. Hey, that's really easy, isn't it? That's the first thought for us. Oh, but I only need names of length 4, not everything. Okay, no worries. Name is going to be of type length over here, the value of length, and is equal to, or if it's JavaScript, it's 3 equals. Maybe another language will have 4 equals, who knows? But the point really is, then we put equals to 4, and then what do? Then we print it. Well, that's great. That's all the names of length 4. Oh, but wait a minute. I want the names to be comma separated. Well, of course, that's really easy to do. I can print them comma separated. Oh, but I want them all in the same line. Well, sure, we can all put them on the same line. And then you realize there's a stupid comma in the end. Has anyone faced this problem before? Yeah, every one of us, right? How did you feel when you ran into that problem? You're saying, it's not happening to me, right? Because it's a simple thing to do, and yet it's so complex. And 15 minutes later, you are still writing code. And in the meantime, the boss comes to you and says, how's it going? You want to strangle them, isn't it? Because you're writing this code, and it's still going, and you're not done with your work. And then we kind of wonder why we don't go home in time, isn't it? And we sit there, and we keep writing code. And that is the whole point is, this is primitive obsession. This is a very low-level code, and that's what we've been doing for quite a while. But the question I want to ask you is, have you written code like this? Because I know everyone has written code like this. But what I will ask you is, how does it feel to write code like this every day? I'll tell you how it feels. It feels dirty. When you finish your work and go home, and the kids come running towards you, you say, don't touch me. I got to go shower first, right? That's how you feel about it. It's a very low-level abstraction, takes a lot of effort to write the code. So what can we do about it? How can we move forward in this direction? And you don't want to be writing code like this every single day because it takes a lot of effort, a lot of time, a lot of energy, and we still want to release production code and create value as soon as we can. So what can we do about it? Well, some things are really fundamental and really hard to change. It's important for us to understand what those things are in our field. For example, Turing completeness. Almost every language that's worth programming in today is Turing complete. But Turing completeness doesn't tell you anything about how expressive your code is. It doesn't tell you about how easy it is to work with it. It doesn't tell you if the code is maintainable. It doesn't tell you about efficiency. It doesn't tell you about performance. It doesn't tell you about a lot of different things. So Turing completeness is a very low bar for a language to pass through, and then there's a lot of things we have to consider after that point. Then, of course, von Neumann bottleneck. We have to still deal with that memory and accessing data from the memory into our processors, and that's only going to get really hard as time goes on. But the question really is, where are we going in terms of programming languages? Does anyone remember what year object-oriented programming was introduced? Well, if you really look back in time, the year when object-oriented programming became really popular, like nobody questioned about it, and everybody started using it. That was the year approximately 1990. So about 1990 time frame, I remember as a very young programmer, like I said earlier, I've been writing code for 35 years. And back in the 80s, I was a very young programmer. And I would look at people and see all this war. Some group of people will say, object-oriented programming rocks, it's amazing. Another group of programmers will say, object-oriented programming sucks, we should never use it. And they were just fighting constantly with each other. And then suddenly, everything quieted out. People quietly started programming with objects without even questioning it. That year was about 1990, plus or minus a few years. But if you really think about when object-oriented programming was actually created, it was created by these two guys, Dahl and Nygaard. These two are two Norwegians who first created object-oriented programming. And this was created in Norway, and this was introduced in the year 1967. Kind of scary, isn't it? It was 1967. Now think about this for a minute. If object-oriented programming was a human, it had a terrible childhood. Nobody wanted to deal with it. And then when it turned 23, it was suddenly, hey, handsome, do you want to hang out with, right? And this took 23 years for adoption. Things don't change so much quickly as we think it is, and it took a good 23 years for us to really accept OOP and start moving with it. So right from 1967 to mainstream in 1990s, that's a very long journey, about 20 plus years. Now think about that. 20 years is when a child is born and has legal rights in almost any country, isn't it? That's a very long time. Goes through adolescence, toddler, adolescence, and becomes an adult. That's a very long time. What about functional programming? Well, it turns out functional programming has been around even longer than object-oriented programming. But when was it really created? Well, even before that, we can think about lambda calculus, because lambda calculus are the underpinning of the functional style of programming. So the question is, when was lambda calculus created? It's kind of scary. Everyone here knows of Alan Turing. This was Alan Turing's professor, Alonzo Church, and he created this in the 1930s. Can you imagine something that was created in the 1930s is just about getting to be exciting? Good 90 years later, we are like, hey, this is awesome. We should maybe do this, isn't it? And when you think about it, 90 years for something to be accepted and maybe possibly become mainstream, that's pretty scary, isn't it? So when I hear people say that things change really fast, I always ask them, what are you smoking? Because in our field, things don't change really fast. It changes really slow. We just have this perception that things change really fast. What they mean by changing fast is 25, 30 years, that's a very definition of the word fast. So things actually change relatively slow in our field than we are willing to accept it. Well, the question then is, why does it take 20, 30 years? Why does it take so long to adopt? And I kind of gave a hint about it earlier, what the year 20 years really means. And there is a really good reason for why things take 20 to 30 years for things to change. One of the reasons for that is we need to really look back to learn about these things. As George Santayana said, those who cannot remember the past are condemned to repeat it. So learning from what happened in the past can help us to prevent some problems in the future. So let's ask the question, why do things take so long? The reason is programmers don't adapt too well. And this is, I'm not talking about the select few people that you may know. You know, you are probably an exception. Think about this for a minute. Today is a Saturday, and it's about 2 p.m. on a summer, beautiful summer day. Instead of being out there enjoying the beautiful world, you are sitting here and you're listening to an old man. You know, what does it tell you? It tells you have no life. And it also tells you that you're absolutely passionate about programming. So you are the exception to this rule. But we are talking about 10 million Java programmers out there and even more programmers in the world. And they don't care about stuff like the way you and I do. And that is one of the questions to ask. Why do things take a long time to change? One of the reasons is programmers don't adapt too quickly and too well. And we take changes in bite size, a little change at a time. And habits are really too hard to change. It takes a new generation. And I realized it one day when a few years ago, I was giving a keynote in a conference. And just like a stage like this, I spoke. I had a really good time at the conference. I finished my talk. And as soon as I finished my talk, I got down and sat down in one of the very first chairs in the room. And there was a lady sitting next to me, and she turned over to me and said, "Hey, that was a really good talk. Thanks for coming." I said, "Absolutely. Thanks for being here." And she said, "Well, I've graduated with a degree in computer science. I have a master's in the field. I've been working for about 2 years," she said. And I thought to myself, if a person has, graduated with a master's degree and is working in the industry for 2 years, you can guess what their age is. It's not really that hard. So I kind of knew, what her age is. That's great. Then she said, "Can I ask you a personal question?" I said, No. We don't do personal questions. Thanks for coming for the conference. I'm glad you came. We are done." And she said, No, please. I have to ask you just one personal question. If you would just answer this one, it'll make me very happy. And I said, "Okay, you're allowed to have one personal question. What's your question?" And she said, "What year did you graduate from college?" I said, No, we don't do this. I'm not going to tell you what year I graduated from college. Thanks for coming. We are done. She said, No, please. You have to tell me what year you graduated. So I told her what year I graduated. And the minute I said the year, her face blossoms. And she says, "Really? That's the year I was born." And I kind of looked at her and said, "Can you do me a favor?" She said, "What can I do for you?" I said, "Can you reach over and get the cane for me? I need some help walking." And I went back to the hotel that evening. I was thinking about it, and I said, "My goodness, I am sitting next to a colleague in the industry who was not even born when I finished college. And all my years of experience is her childhood. And how much fun it is to work with somebody from the next generation in the field." And I started thinking, this is amazing, because this is one of the things to think about, and it immediately clicked in my mind why it takes 20, 30 years for change to happen. And the reason is, when you're very young, you are very active. You're like, "Oh my gosh, I can try this, I can try this, I can try this." And then when you get a little bit more experienced, you get comfortable, everything works for you. And somebody comes to you and says, "Hey, we can do something different." You're like, "Shut up, just sit down. We got work to do here," right? And then 20 years goes by, and what do we do as the guys who have experience? we get so comfortable doing things. And we say, it's life as usual, keep everything in balance, let's keep going. And these young people come over and say, we could try this, we could try this. And then you kind of look at them and say, come on, what did you drink this morning? Take it easy, right? And then I realized change happens because there's new thinking. Change happens because there's new energy. Change happens because there's new thought and idea. And then I realized this is just amazing because nature is brilliant. Because what nature does is as time goes on, it's built in with automatic garbage collector. It pushes people like me away and brings the next generation, only for them to be pushed away in the next about 30, 40 years. And so there's a reason for the cycle that goes on every 20 to 30 years because nature has a built-in automatic garbage collector. How boring the world will be if the old guys sat around forever and did the same thing. We need young people to try new things, to make their own mistakes and learn from it as well. And to me, that's really rewarding. And I'm not saying everybody who's old is adamant and stuck in their ways. There are exceptions to everything, absolutely. But in general, though, it's the new energy, the new thought that makes really good difference as well. And there's a reason why things actually take time as things move in that pace. But we are poised for another big change in our field. This actually started in the year 2003 to 2006 timeframe. So what did happen in 2003 to 2006? Well, it turned out between those 2 years, we had a few things that changed for us. The first is the multi-core processor. Can you imagine the engineer walk to his boss and say, it ran really fast before it melted? So we started realizing we cannot pack more into a processor mostly because of heat generation, and we had to really create multi-core processors. The second thing that happened is the business demand for big data and mobile devices as well. So as things change, how do we program these things moving forward? And if you really look at today, we got modern demands for what we do. We are living in the world of cloud computing, big data, microservices, IoT, machine learning, AI. And the question is, how do we program all of these things moving forward? We have some answers already. We have NoSQL, which is trying to really provide us a much better, lighter way to program these systems for persistence. We have the MapReduce, which is extremely prominent. We have reactive programming that's coming really successfully. A lot of databases are becoming reactive. A lot of applications are becoming reactive as well. So we are looking at a lot of changes already in the field. But if you really look at the web that we are developing, we are still struggling with what I would like to call as the old web. So what is the old web? The old web is predominant today, and it is built on the stateless request and response idea. Now think about this for a minute. You make a request, you get a response. You make a request, you get a response. You make another request, you get a response. But what's really wrong with this idea of programming? Well, what is wrong with this is there is no context because of statelessness. Now, we all argue, is state good or state bad? And there's no real good answer or right answer. But imagine what happens when it's absolutely stateless. I'll give you a real-world example of how that feels like. Suppose I come to you and say, did you go to the movie yesterday? You say, oh, yes, I went to the movie yesterday. How was it? How was what? Like, really? Well, we have this conversation we carry with us, isn't it? So if I ask you, did you go to the movie yesterday? You say yes, and I say, how was it? You should talk about the movie because there's a context in the conversation. But not if it's a web, isn't it? Because every request you make, you got to establish the context. And that's tiring. That's a lot of work. And it's not really effective for what we do. But what is the answer? The answer is nothing new, yet it's not prevalent. And the answer is to rethink about this. So rather than having this poor separation of concern, what if we have the new web where we can do continuations? So what in the world is a continuation? A continuation is where you can build applications that have a conversational state. So I come to you and say, did you go to the movie yesterday? You say, yes. How was it? It was fantastic. What did you like the most about the movie? Notice how we have a conversational state and you remember where we left off. In fact, you and I could be talking about something during dinner and we go off, we have a good sleep. The next morning we meet at breakfast, we can continue where we left because we remember what we spoke. In fact, sometimes you don't even need words to communicate. You could be just sitting there and something could happen and you could just smile across the room at your partner and your partner may smile back at you. I know that sounds really romantic. But the point is, when we share a context, the communication becomes simpler and easier. When we don't share a context, it becomes burdensome and tiring. So what if a web can be built around a conversational context? We're still farther away from doing this in a lot of languages, but I'll give you just a glimpse of how that would feel to what we want to do. So here is an example. I'm going to show you this example in JavaScript. I know that's a bit scary, but I think we can learn from every single language out there. So let's take a look at an example here. So I'm going to say constant. We'll call it as fetch is equal to function right here. And I'm going to simply say in this case, let's simply put an output that says entering. So that's a very simple case. As you can see here, it simply says entering. Now I want to simply say for, and let's go ahead and say over here is an element of the fetch function. We'll call this function, and what I want to do within the loop here is simply print the element. But where in the world is the element? I'm going to say yield 1, and I'm going to run this code. So notice it says entering, and it printed 1. But what I want to do next, though, is I want to continue with this code and say, and then, and I'm going to simply say yield 2. When I run this code, notice the call to the function did not go to the beginning of the function. It entered right in the middle. Hey, that's a conversational state, isn't it? Because it knows where you left off, so it knows where to go back. And then, of course, you can also say, for example, and then more, and then you can say yield of 3, if you will, and when you execute the code, you can see how we can continue with this conversation. So what if we can build applications that can maintain this kind of conversational state to what we do? Now, this is an idea that's going to become really prevalent in almost every single language and library in the next 4 to 5 years. If you're a Java programmer, you may wonder, how do I do this in Java? Well, Java is going to come, the JDK is going to eventually have a project Loom, which is working on several of these ideas. But continuations are going to be in Java in the next about 4 to 5 years, but Kotlin already has that. So what's a continuation? Continuation is a data structure. The continuation data structure captures the current state of your object. Now, this was really hard to understand a few years ago, but it's a lot easier today because a continuation is just a closure. What is a closure? A closure is a lambda expression that can capture the state of its surrounding. So what if every continuation becomes a closure where when you call it, you return a tuple, where you return a data and a closure to go with the data. You consume the data, and then you fire back right into the closure, and you can continue your operation. So in a sense, what languages can do behind the scenes for us is they can take the code like this, and they can return the value 1, but they can capture the rest of the code into a continuation, into a closure, and return it. So when you make a call back, you continue from line number 5, and then it returns a tuple, if you will, of the value here, along with the rest of the code as a closure. So this is something we can actually implement pretty effectively to have a conversational state moving forward, and that becomes really easy to work with. So this is one thing I'm really eagerly looking forward to, is where we can start programming with continuations really effectively moving forward. So you essentially save the execution state and then return back to the point where you left off to continue forward. So languages should make such things very easy for us. So language should make simple things simpler, and they should make really hard things manageable. In that regard, how do we really benefit from these languages? So for that, language must promote higher level of abstraction. So the very first thing I want in a language to give me is a high level of abstraction. The second is composability. And the third is being able to do declarative style. Let's examine these things a little bit further to get a feel for it. First of all, I want the language to be really expressive. What does it mean to be expressive? Expressive is where you can convey your idea very fluently without putting too much effort. A verbose code is where you have to write a lot of stuff to do simple things. An expressive code is where you can fluently write less code and get done with it. Let's take an example of this to get a feel for what does it mean to create expressive code. So here I am in Java, if you will, and I want to read a file in Java. How do we read a file in Java? Let's say I want to read the same exact file in which this code is sitting. So first of all, you start with new, and then you would say something like buffered reader, and then you would say new file reader, and then you would specify the file name. For example, this is going to be sample.java, and you know this is not going to be going well because this is going to return a reader for you. And then once you get the reader, what do? You are going to then go back here and say while, and then you're going to say, define a string. You can say data equal to null, and you know null is a smell to begin with. Then you say data is equal to, and then what do? Reader.readline, and then what do you do after that? And then you say is not equal to null. You know where this is going, right? And the minute you go this route, you realize you have to put 20 try-catch blocks around it, and by the time you are done, you are like tired. You don't remember what you came there for, isn't it? This is far from being expressive. This is tedious. This is, why should we do all this work? Why can't it be really easier to write code? Let's give it a try. So I'm going to go back here. This is going to be a code I'm going to write in Kotlin. So I'm going to say print line java.io.file. The name of the file is called sample.kts, and I'm going to call read text on it. So I'm asking it to read the text from the file and display it. And so that's a code that is reading the code itself. As you can see, that didn't take a whole lot of effort at all. And what if languages can be like that, where we can just get in, get the work done, and move on? You don't have to be struggling with it, and that becomes a lot easier. Well, one other thing that is going to come in Java in the next 3 different releases is a feature I really like a lot. It is called pattern matching. Well, Java doesn't have pattern matching today, but it's going to have it pretty soon. But let's get a glimpse of what pattern matching looks like here using Kotlin. So I'm going to call process with a 1. I call process with a 15, and call process with a hello. So I want to process some messages that are coming towards me. So I'm going to say process. It takes an input, which is an any input given to me. And I'm going to say when input, I don't know what I'm really looking at. So I'll say else, and I'll simply say whatever. So when I run this code, it says whatever for all those 3 things, as you can see. But I can say here is an int, and I can simply say got a number. So when I run this code this time, notice it says got a number for the first 2, and it says whatever for the last one. But look at the expressive power of this code in pattern matching. Let's go a little further with this. What if I say in 13 to 19, and I'm going to print out a teen? So when I run this code this time around, notice it says a teen for 15, whereas it says a number for 1 and whatever for the last one. We can go a little further. We could say over here is a string. And in this case, I'm going to go ahead and print out got a string. And when I run this code, it says got a string over here. However, I want to be able to know what the length of the string is. How do I know what the length of the string is? Let's give it a try in Java, if you don't mind, for a minute. So I write a function in Java. Let's call it static void process. And this takes an object input. And what am I going to do here? I'm going to simply output the input. So if I were to call the process function over here, let's say with the value 1, and call process with the hello over here. So this is Java code. But I want to print the length of the string. So what do? In the case of Java, I'm going to say input.length. Will that work? No. Why not? Because length is not a property of an object. You know that. So when I run this code, it says, what are you talking about? It doesn't understand it. So what are you going to do? I'm going to say, aha, I got an idea. If input is an instance of string, then what am I going to do? I'm going to go ahead and print out got a string. So when I run the code, it says got a string. But I want to say a plus, string of length. And what is the length of the string? I'm going to say input over here, input.length. Will that work? No. Why not? Because Java says you can't just call length on an input because it's an object. So what do you have to do? You have to take this one and you have to say string and you have to write code like this, isn't it? So when you write code like this, what does the compiler say? The compiler gives you a pat in the back and says, good job now, right? Now, does anyone remember what this feature is called here? Yeah, people call it casting. I call it punishment. That's what it really is, right? Java punishes you and says, you better do this. So at some point, I think about this and ask the question. And this is a question I always wonder when I start programming. And the question I ask is, does the compiler work for you, or do you work for the compiler, right? So I always kind of wonder that. In some languages, you work for the compiler. The compiler says, more code, and you sit, write more code. And then it comes back and says, keep going, are you done yet? And you're like, shh, are you happy now? Not yet, keep going. And that's what you're doing. This is not expressive. This is excruciating, isn't it? It's a lot of effort to write code in such a mode. Here's the good news. Java is going to have a feature that I'm going to show you next. And that feature is available already in Kotlin, which is called a smart casting. Let's take a look at what smart casting actually looks like. So when I go to the code in Kotlin right now, I'm going to run this code. It says got a string, as you can see right here. And I'm going to say of length. But notice I put a little dollar and say input.length. And I just call that right in there, just like that. And it gave us the result, as you can see. It says that input is of length, and it displays the length for us without much effort at all. But make no mistake, if you go up here, and if you said input.length, that would be an error. You cannot do that because length is not a property of object. You cannot do that. But on the other hand, you can call a length over here because the language knows that you have paid your dues already. Hey, you said it's a string, so now I know it's a string. But here's the good news. You can do this in Java as well, maybe in the next few years, because these things remove ceremony in the code. These remove the verbosity in the code and makes it a very pleasant experience for us to write the code. So that is one example of what we can actually do in terms of making the code expressive. The second is composability. You want the code to be very highly composable. So what does it really mean to make the code composable? And what are we really trying to achieve with composability? The composability really is where you want the code to flow through a series of transformations rather than state mutation. That's what you're really trying to do. So I'm going to go back to the code we wrote a few minutes ago where we were trying to really struggle with the code for taking the names and transforming it. So what I want to do is maybe we can apply composability right here in Java. This is one of the reasons why I love what Java 8 has done for us. We can nicely do that in to realize composability. So let's try to take a look at an example of this to see how we can do this. So notice this code we saw a few minutes ago, and it still was not solved after all. So what can we do instead of all that extra work? Can we make this a lot simpler? And the answer is yes, we can make it simpler. We'll first of all bring in the collectors into here. Then what we will do here is we'll go ahead and say that we will use the functional composition output. We'll say names.stream, which is an internal iterator. And then we will say filter given a name. I want to say name.length is equal to 4. And then we'll perform a map operation where we'll say string to uppercase. And then finally we'll say collect. And we will simply collect joining. And we will simply say joining using a comma. And then we will simply produce that result. So when I go back and run this code, you can see there's no stupid comma in the end, and the code is a lot more easier to work with. So this is an example of the transformation, as you can see here, where we have the functional composition, where we take the names, we filter all the names of that length, and then we transform the names, and then we collect it with a comma separation into a string, and then we eventually print it. That's an example of the compositional aspect. So when we start programming with functional composition, it becomes easier to understand the code. It removes the impedance. The code begins to read like the problem statement. When the code begins to read like the problem statement, it becomes a lot easier to work with the code in general. So as a result, we want more of these things in languages where we can use this kind of programming and not as much of the imperative nature of doing things. Then, of course, you want the code to be really efficient. Now, how do you make the code efficient? Sometimes it's to improve performance, we will try to introduce multi-threading. But oftentimes that's really hard. But what if multi-threading becomes almost trivial to do? Like, for example, if this were a really large collection, if this had a lot of computation to do, you could simply say parallel stream, and you can run the code in parallel rather than running it in sequential. So that becomes almost effortless to make the code more efficient, at least from the concurrency point of view. So you can try to really use some of those capabilities. Again, languages like Java has moved us in the right direction, as you can see in that point. But then, one of the things I feel is extremely important in the world we live in today is asynchrony. Now, if you think about it, we have lived in the world of parallel computing in Java and C# and C++ for a long time. We create multiple threads. Languages like Java predominantly are asynchronous. But today we live in a world of microservices. And in a world of microservices, more than parallelism, I think we should really embrace asynchrony. But how do you really make the code asynchronous? If you write the code sequentially, it's easy for us to understand, easy for us to conceptualize. But once you do, if you then go back and change the code entirely to make it asynchronous, and the code turns into a monster, it becomes really hard to understand. It becomes really hard to maintain it. Wouldn't it be so nice if the synchronous code and the asynchronous code look almost the same? Well, I want it to look almost the same, but not exactly the same. That's why I'm using the word almost seamlessly. I don't want it to be totally seamless. I want a little bit of seam, like you see in the pant, so you know that there is a boundary, but it doesn't look ugly. But why do I want the seam in the code? Because a seam in the code tells you, the programmer, that you are going through a shift in the semantics. Understanding the shift in semantics is very important for correctness of code. Let's entertain this thought with a real quick example here. So I'm going to give you an example here in Kotlin again. So I'm going to say over here, let's go ahead and import over here Kotlin, let's say coroutines.star for a minute. I'm going to create a function called task1. And all I'm going to do in the function task1 is simply print out right here. We'll say entering, let's say task1. Okay, great. Then I will simply say exiting task1. But then I'm going to put right in the middle a call to the yield, just like you saw in Java a few minutes ago. So that's my task1. I'm going to call task1 real quick here just to execute this little code and see what it's going to do for us. So, but this is going to be an yield call that I'm going to call in here. But what does the yield call tell us? It says suspend function yield should be called only in a suspend function. Now, I want you to look at this error. We'll come back to this error in just a few minutes. So without it, I'm going to run the code right now, and you can see that it says entered and exited. Let's do this one more time. I'll leave the error. We'll come back and fix it in a few minutes. Then I say here is task 2, and this is going to be task 2. So I want to call task 2 right in here. But I'm going to say over here, run blocking. Let's just do this for a second. And I'm going to call these two functions here within the run blocking. So when I run this code, you can see that it enters 1 and exits 1, enters 2, exits 2. No surprise in here. However, what if I want to return something from this function? So I'm going to say this returns an int. Let's simply return a 1. This returns an int also. Simply return a 2. So I want to receive those values and use them. How do I do that? So I'm going to say result is equal to, and we will get the results of these two calls, and we will simply print out results, and we will go ahead and print out result 1 over here, and then we will also print over here the result 2. So very simple example, as you can see in this particular case. So when I run this code, it simply says entering 1, exiting 1, entering 2, exiting 2, and then results are 1 and 2. However, what I want to do is I want the functions to be asynchronous. So I put yield, and I put yield over here. Just look at the code for a minute. I just added a yield in the implementation of the method. I mean, that is dangerous in my opinion, because the meaning of this code is very different now. And if you don't see the difference in code, programmers can commit errors. This is why I say almost seamless. So when I run this code, notice it gives us an error saying, hey, watch out. You're doing something very different semantically. Don't be surprised about it. So what are you going to do to fix it? I'm going to say suspend over here, and I'm going to mark this function as a suspend also. So when I run the code this time, notice there is no error. This is what I meant by almost seamless. So when you look at the code, oh, that's a suspend function. Something is going to happen here. I better be careful about it. It gives you a semantical difference. Now, look at the sequence of the call. Result task 1 and task 1 and task 2 and task 2. That's pretty darn synchronous. But we're going to make this asynchronous. How do I do this? I simply go back to this code, and I'm going to say async right here. And then I'm going to close these two right about here. So we made those two calls asynchronous. Then I come in here and say await on this one. And I come in here and say await on this one as well. So when I run the code this time, very little change, but the structure of the code is exactly the same. But notice the sequence now. We entered into both the functions at the same time. And we have not exited the task 1 yet, but we are in task 2 right now. And then, of course, we exit both of them, and that shows that it's asynchronous in its computation. So the point really is, you didn't change the structure of the code to make it asynchronous. You had to make minor changes to it and put a few semantical cues in there, and then off you go. And that becomes a lot easier to work with. So in a sense, how can we prepare for the future of programming? Well, to answer this question, I'll give you a small anecdotal evidence to this. I mentioned that I program in 15 different languages. But part of the reason I do that is I'm curious to learn. But part of the reason I learn different languages is I want to be able to think very differently. But I want to mention to you really quickly one experiment. This was conducted in Chicago. And what they did was in Chicago, they brought together very small children. And these very small children, they were toddlers and very young. And there were two groups of children. One group were children whose parents spoke one language, and everyone they interacted with spoke the same exact language. So these children were introduced only to one natural language, for example, English. The other group was children whose parents also spoke the same language, but they had nannies who spoke a different language. They had children at school who spoke a different language. Or they played with children in the evenings who spoke a different language. So one group was children who were exposed to only one language. The other group is children exposed to multiple languages. The second group of children didn't speak multiple languages at that point, but they were exposed to multiple languages during the day. And what they did was the researcher, imagine I'm the child, and the researcher was sitting right where you're sitting. And the researcher asked the question, how many computers you see in front of you, as an example. The researcher asked how many objects, how many apples, how many bananas you see in front of you. The gentleman here has a computer, so I'm able to see this computer right here. When they asked the question to the child, imagine the child is sitting where you are sitting, and imagine I'm the person asking the question, sorry. So when the researcher asked the question, how many computers do you see? The child who was exposed to one language, for example, said 2 computers, seeing the computer that this gentleman has on his lap and seeing the computer I have over there on the table. On the other hand, when the researcher asked the question to a child who is exposed to multiple languages and said, how many computers do you see? Suddenly, these children looked around the room and filtered out the computers the person asking the question will not be able to see and says 1, for example. This was strange because consistently they were seeing this result, that the children who were exposed to one language will include all the objects they are able to see, whereas children who were exposed to multiple languages always filtered out the things that are behind the person who's asking the question and only talk about what's really shared. This led them to believe that children exposed to multiple languages have more empathy. They begin to think about things from the point of view of other people. Well, I'm not a natural language specialist, but I can tell you that I'm a huge fan of programming languages. And having worked with multiple languages, I can tell you that is true in programming languages. Because when you program in multiple languages, you begin to think very differently than when you program in one language. So if anybody here says, I program in one language, you got to put an end to it. Because programming in one language is extremely limiting to your future. Because your mind is much better when you're exposed to diversity of programming languages. And again, just because you know Java, you cannot learn C# and count it as 2, because the languages are pretty similar to each other. They got to be very different languages. How different? I say the quality of a good language is it should make you cry when you start learning it. You got to kick, you got to scream, you got to cry. Because learning to me is like peeling an onion. Now, when you peel an onion, there are 2 things that happen, isn't it? When you peel an onion, you see there are more layers to peel. And you know what happens when you peel onions? You begin to cry. That's correct. And good learning makes you cry. Mostly, it's a tear of frustration. But when you're done with it, it turns into a tear of joy. And if you're not frustrated when you're learning, go pick up something else to learn because it's not significantly different enough. So the question is, how do we really get there? Well, the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas we've been exposed to. So if you are exposed to very many diverse ideas in your day-to-day experience, you will learn things very quickly. But if you are not exposed to diversity of ideas, then your mind throws a fit at you. The minute something is given to you, you reject it and say, no, that cannot be good for me. I'm really comfortable doing what I'm doing. That looks so different for me. So this is one of the reasons why we have to really get out of our comfort zone and start learning very different ideas and very different viewpoints, and that can help us a great deal. So the diversity of ideas is extremely important for our ability to learn and adapt as we move forward. So, learn different languages, but not to use them all, but to be able to adapt to the change really quickly and easily as languages we use evolve. And this is one of the most important things I want to emphasize is when Java, imagine you're using Java, and Java evolves, you'll be really quick in learning what Java has because you've been exposed to these ideas in other languages. So it turns out that languages don't have entirely new things. Languages kind of borrow from each other. So when I started learning C#, when I saw the yield keyword in C#, my question was, how is yield in C# different from one in Ruby? Because I've been using Ruby for a while at that point. Then when I saw yield in JavaScript, my question was, how is yield in JavaScript different from yield in C# and in Ruby? Similarly, when I got exposed to Scala, my question was, how is the actor-based concurrency in Scala different from the actor-based concurrency in Erlang? So learning these languages really reduces the time for you to learn new things. So don't wait for the future. Here's the fun part. It is already here. Now is the future. And we can be ready for it by diversifying our knowledge portfolio. And as a result, we can accelerate our ability to learn new things. Hope that was useful. Thank you so much for being here. I'll be delighted to take your questions. And I was told that you can ask your questions in any language you want. You can ask your questions in English, in Portuguese, Java, C#, any Python. And I'm told that if it's a language I don't understand, it will be translated for me. So I'm very eager to hear your voice, hear your thoughts, your questions, your comments. So please proceed. We got the microphone over here as well. Don't be shy. There we go. Thank you.